Okay, we can start. So, wait. Forse l'ha preso il professore, non so. Okay, so thank you for being here, and I really thank Professor Tina Eliassi-Rad for having accepted our invitation to be in Padova. Tina is an associate professor on computer science at Northeastern University in Boston. She's also a core faculty member at the Northeastern University Network Science Institutes, and her research is rooted in data mining and machine learning, and spans theory, algorithms, and application of big data from network representation of physical and social phenomena. She's over 70 peer-reviewed publications and has given over 180 invited talks. So we are very pleased to have her with us. And today she will talk about just machine learning in a just word, maybe.
Thank you. I guess I don't need that, right? I have this. So thank you all for coming, and thank you, Samir, for inviting me. If the title seems odd to you, it's on purpose. So am I saying just machine learning as in justice in machine learning? Or am I saying, oh, it's just machine learning, don't worry about it? You can decide at the end of the talk. So I know AI is a big buzzword nowadays. So whenever somebody talks to you about AI, the first thing you should ask them is, which AI are they talking about? Are they talking about systems of agents that think like human beings, or are they talking about systems of agents that act rationally? And as we know, human beings don't act rationally, right? The other thing is that when people say AI these days, they oftentimes mean machine learning. But AI encompasses many subfields: knowledge representation, planning, robotics, vision, automated theorem proving. And so again, to hold their feet to the fire and say, exactly what are you talking about? Now, this lecture is about ethics in AI. I like this taxonomy that Julia Bossman came up a couple of years ago. And obviously, I won't have time to go through all of them. I will focus mostly on the sexist, racist robots within the context of machine learning. You're welcome to go to the website and read her excellent article. My slides are up on the web. At the end of the talk, I will have a URL for you that you can go and download them. So machine learning, hype, a lot of hype around it, a lot of money around it. The phrase was coined way back in the 1950s by a very prominent scholar, Arthur Samuel. And he defined it as the field of study that gives computers the ability to learn without being explicitly programmed. And the very first machine learning algorithm was the Samuel's checker playing program. You see it here, that's Samuel. And it wasn't really learning the way we think of learning. What it was doing is it was memorizing every state that the game was in with the terminal reward of having been in that state. Now, machine learning supposedly is this nice interdisciplinary field. And if I don't have your field here, my apologies, I didn't want the flower to get too crowded. So that's in theory. In practice, the machine learning is more like, scared my own. Machine learning is more like this. And how many of you have seen this XKCD cartoon? Very few of you. So A says to B, this is your machine learning system. B says, yep, you pour the data into this big pile of linear algebra, then correct the answers on the other side. A says, what if the answers are wrong? B says, just stir the pile until they start looking right. So this is a little cynical, but there has a grain of truth to it. The one thing I want you guys to pay attention to is the words right and wrong. So right and wrong here don't mean anything about ethical rightness and ethical wrongness, right? It has nothing to do with normativity of what you ought to do. It's just about, for example, accuracy. So moving forward, Tom Mitchell, who is a very famous machine learning professor in the United States, he was the guy who created the machine learning department at Carnegie Mellon University way back before machine learning was a huge thing as it is now. And he has a textbook, and if you are a novice in machine learning, I highly recommend reading this book. It's very easy to read. The book came out in 1997. When I took my machine learning class, I was one of the guinea pigs of reading preprints of this book. He defined the well-posed learning problem as a triple. You have a task, you have experience, and you have performance metrics. And he defined it as follows. A computer program is set to learn from experience E with respect to some task T and some performance measure P if its performance on T as measured by P improves with experience E. Experience E here is data, right? So you all have, for example, a spam filter on your email, right? And so the task is to filter out spam from non-spam. The experience that the computer program sees is you labeling things spam and not spam. And the performance could be accuracy, right, of the computer program, naive Bayes or whatever else if you're into specifics, right? So when machine learning goes wrong, it's usually because one or more of these things have gone wrong. So let's talk about this. Let's talk about the task. The first thing is, again, this, I'm not sure what's going on. Yeah, let's use that because this thing seems to jump up and down. Could you turn this off? Thank you. Excellent. So the first thing to know is that is the learning algorithm actually learning for your task? So back in the 1980s, the United States Department of Defense wanted a classifier that could classify tanks that were camouflaged versus tanks that were not camouflaged, right, in woods. Very simple, right? I have a jungle, I have forest, and I want to know if a tank is camouflaged or not. It seems like what the classifier actually learned was whether it was sunny or not whether it was, whether a tank was camouflaged or not, right? The data was such that all the tanks that were camouflaged was more cloudy, and when it wasn't camouflaged, it was sunny. So that's what the program learned. The other one is bad science that recently came out of Stanford, where they said, oh, we could tell from your picture whether you are homosexual or not, whether you're gay or not. And it seems like what they learned, because people are trying to re-engineer what actually happened, they learned that gay people tend to have photos that have better lighting. That's what they learned, right? So one is being careful about, is the machine learning algorithm actually learning for the task that you care about? And so hold on to that disclaimer and let's move on. So what are some of the tasks that are popular right now in the area of, for example, ethics and machine learning? The two are assessing risk and ranking. So you may say, why these two particular tasks? One is because machine learning people know a lot about them. I know a lot about assessing risk. It's an easy prediction task, right? What is the risk of Tina committing a crime versus the risk of Bob committing a crime, right? So these are very simple classification algorithms. Usually, you know, you go from 1 to 10, and then if it's 10 and upwards, it's bad, and 4 and less, it's good. And the other thing is that it's low-hanging fruit, and human beings really understand them, right? If you think about a judge gets, oh, risk of Tina committing a crime is high. Okay, great. Tina goes to jail, right? Or risk of Tina defaulting on a loan is high, so Tina doesn't get a loan, right? So these are very simple tasks that machine learning people know a lot about. And if you look at the literature for fairness in machine learning, there are tons of paper there. It's not clear whether any one of them is going to, or even a collection of them is actually going to make any progress in terms of the actual real problems, in terms of human decision making with algorithms. So these are the two tasks that are really popular: risk assessment and ranking. The ranking is because of the web, right? So there's been a lot of work in terms of ranking web pages and having both diversity and utility and so on and so forth. So there are issues in terms of assessing risk. One has to be careful about this. There have been a few impossibility results. For those of you who don't know, impossibility results is basically you can't have your cake and eat it too. Cova at Carnegie Mellon back in 2016 said you cannot have a model that satisfies these 6 properties. So suppose I have my population, I divide them into A and B. A are males, B are non-males. And so they're mutually exclusive. Suppose that my non-males have a higher probability of getting breast cancer. So that's the first one, unequal base rates. Then she said that I cannot have these 4 things that I care about, right? I cannot have statistical parity, that is the probability of, and this is also given, sorry, the statistical parity are also given, which is the probability of, for example, having cancer among non-males of the classifier saying it's a cancer is the same as the classifier saying cancer among the males. And then you can have these 3, which is precision parity, true positive rate parity, and false positive rate parity. Kleinberg, around the same time, John Kleinberg at Cornell came up with, okay, well, what if I got rid of the statistical parity, but I have an imperfect classifier? That is, what the classifier predicts is not always the same as the ground truth, as it's called. And then recently, Feidelson and we have come up with a new result which says that you don't even have to have mutual exclusivity. So for example, if you have a population that has blacks and whites and you have somebody like Obama, well, he is both white and black, and that is not a constraint here. You will still have the impossibility result of if I have unequal base rates and if I have an imperfect classifier, then I cannot satisfy these 3 fairness or parity measures that I really like. So what has been the fallout from these impossibility results? People have not given up on the risk assessment. They're like, oh, risk assessment, we love it. It's great, we understand it, let's continue on with it. So what they've decided to do is to get rid of one of the parities, right? So which one do I get rid of? Precision parity, true positive rate parity, or false positive rate parity? Or for example, putting bounds on the parities in terms of how far apart they're going to be. Deborah Hellman at University of Virginia Law School has been thinking about what do these parities actually mean. And so she is writing a book about how precision parity really means what you ought to believe in, and true positive parity and false positive parity mean what you ought to do. And she's arguing that if you're building an algorithm, and you're going to get rid of one of these constraints of parity, you should get rid of precision parity. Because precision parity looks at what they call the right-making property. And in our society, oftentimes being a white male is the right-making property, right? For hiring, for loans, so on and so forth. So there are other issues. So if you think about this task of risk assessment, it seems too abstract to have any kind of ethical or normative considerations. In addition, it provides no uncertainty values to the human decision maker, which is very bad, and I will have an example of that. And also, it doesn't incorporate any context. So you all, I know about the COMPAS data, right? This is, and software, so data was collected in Broward County in Florida over 30 years, and there was a private software company, North Point, that had a software called Compass that was being used there to during pre-trial deposition for recidivism, risk of recidivism, and it's over 30 years. Laws and policies have changed during those 30 years, right? But it seemed like the software was not using that. Now, the problem of having no uncertainty values given to the human decision maker are cases like this one. This is from the ProPublica studies. ProPublica is a media company in the US, where a judge actually overturned a plea deal that human beings had come up with because the algorithm said that the risk of the person committing a crime was very high. Right? Now, the incentives of this judge is that if he lets the person out and the person commits a crime, the judge is going to be on the front cover of New York Times. Right? But maybe if the algorithm said, well, the risk of this person committing a crime is high, but the algorithm is only about 65% sure, then maybe the judge would have decided differently. But the fact that a judge completely overturns and disregards what human beings, experts, have decided just seems odd, even for a machine learning person like me, right? I would not want that. So we are working on a new task, and I'm not here to sell you this new task. It's just something we're working on. You could take it or leave it. Usually machine learning people are like, oh, my task is the best, and then in about 2 minutes, somebody else comes with a better task or a better algorithm. Well, we're working with Xindi Wang and Onur Viral. Onur is a postdoc at Northeastern, and Xindi Wang is a graduate student, is to try to learn to place people. So the society tells us which cases are better and which cases are worse. Obviously, first-degree murder is a lot worse than petty theft, right? And so you have the spectrum of better and worse, and now Peter comes, and you want to know where Peter falls, right? Where should you place Peter? Now, if you can place Peter well, then to the judge, to the human decision maker, you can say Peter is between Ed and Bill, and this is my confidence in Bill's placement here. So by doing this, you're taking one of the things away from the judge, which is using algorithms for efficiency purposes. I feel like for human decision making, whether Tina goes to jail or not, something that really affects somebody's life, the algorithm should not be used for just efficiency purposes, right? So what we do here quickly is we have a two-phase approach. The first phase, we go and ask about whether one case is better than the other case. Now that we have these pairwise preferences, we learn a classifier that takes two cases and says, I think this case is better than the other case. And better or worse, again, is laid out based on the laws and the policies of the environment that you're operating in. And then the second place would be to place this new item within the list of things that you have seen. So if you have a new item and the classifier says the new item is worse than A but better than B, you can get these kinds of conflicts, right? And so what we work on is basically we do a simple voting, which is very fast, which mirrors maximum likelihood estimates. So if I have a new item 4 and I want to place it on my spectrum, I ask the classifier, well, how does this item compare to the rest? And then I get these different inequalities, and then, for example, item 4, the new item, is better than item 1. So everywhere below item 1 gets a plus, everywhere before it gets a minus, and then you just take the mode of the interval, and you can have confidence values. So why this task seems interesting is because you can do auditing of cases. So if you have a population and you have broken your population into colors, right? You have red people, blue people, so on and so forth. What you could do is you could say, okay, I have these features or characteristics that are protected, like race, gender, income level, so on and so forth. And what I'm going to do is I'm going to train on, let's say, the red population, and I'm going to test on the red population. And we're calling this normal experiments. And then we have the opposite, where, for example, I'm going to train on the red people and test on the blue people. And that's called the cross experiments that we talk about. So then in this case, I have a fair line. One of the things which is very hard to do is what is a fair model? So in this case, if indeed the society isn't making any difference between the blue people and the red people, then this kind of a normal test and cross test, you would expect that the error of the classifier would be on the fair line, that it did not matter where the experiences came from. It did not matter that the data came from the red people or the data came from the blue people, right? The error that the classifier is making is the same for Tina, right? So we have a fair line, and so then you can measure deviations from the fair line and look at and see, this is on Compass data. Our task was predict the number of days until the person is going to commit the next crime. And you can see that the errors that the classifiers are making are indeed different. That is, the distribution of the errors of the classifier that was trained on the red people, or here the black people, is different than the errors that the classifier is making for the white people, given the same test set. And then what you could do is you can actually measure the difference in error between the two models, one learned on the blacks and one learned on the whites, and try to see who's being favored and who's being prejudiced here. We just did density estimation. And then what you can see is you can see the variances in terms of the differences in the errors, and then you can track these variances through specific subgroups. So here I'm just showing you on race. I have lots of results. You can download it from that website, where you could track this variance, and you see that the variance that you see on the blacks goes to black females. So if you want to audit cases, you should look at the black female cases, because the model seems to make a lot of errors on them. Why is that, right? The variance on the error for the whites, especially white males, is very small, but for the black females, it's very large. That seems odd, right? And then if you follow it through, you see that the black felonies have a lot more variance. The error in the model has a lot more variance than for the whites. And then if you follow it through, you see that a lot of the variance that you're seeing is for blacks between 21 and 25. Which again, these are cases that if you have somebody who's auditing, can audit those cases and see what is going on. Now this seems okay, but one of the things that this task doesn't allow you to do is it doesn't learn how a human being makes a decision, right? So we would like to be able to see whether I can actually learn the human decision-making process. So here, usually people ask me about, well, has anybody done any kind of human experiments, crowdsourcing, basically? And these guys have done, Dressel and Freed, where they went and asked a bunch of non-experts to make decisions about the same data as the COMPAS data. And they saw that the performance of the non-experts were just the same or similar to the performance of the COMPAS software, right? Now, I think this is very bad, right? We have experts that, you know, and so you shouldn't compare to non-experts, you should compare to experts. The one thing that this paper also showed, which is interesting, is that the COMPAS software seemed to have used 137 features. And they showed that with just 2 features, they could get the same performance as the COMPAS software. One was age, and the other one was number of previous convictions. Okay. So let's step back and think about what are the incentives and values of the expert, no, not the non-expert, of the expert human decision maker, right? Should a human decision maker that's the expert care about profits? I was at a bioethics workshop, and there were people there who were telling me in America, with respect to healthcare, it could be a time where the insurance company says, the machine learning algorithm says that Tina needs this course of medicine or this course of treatment. And if the doctor disagrees with that, the insurance company will say, I'm not going to pay for what the doctor is saying. I'm going to pay for what my machine learning algorithm is saying. That is scary. I like the little murmur I heard. Like, you guys don't have to worry about it in Italy, but that's scary to me as a patient that the insurance company may do that, right? The other one is efficiency. I already mentioned efficiency, right? So there are lots and lots of cases, and the judge is just trying to sort through them, right? If you think about risk assessment, really what it's doing is just sorting. Good, bad, good, bad, good, bad, good, bad, right? That doesn't seem reasonable when you're really thinking about, okay, this person should go to jail or not, right? The other one is accuracy or reliability. So accuracy, again, is a funny term. How do you define it? Fairer decision, whatever that fairer is. So what are the incentives of the human decision maker? Should the human decision maker care about the interpretability of the machine learning algorithm or the explainability of the machine learning algorithm? Andrew Gellman, who's the statistics professor at Columbia, recently had a really nice blog post about interpretability versus explainability. Interpretability is, I want a white box model. I want to be able to look and see how the model made its decision. Explainability is where I have my input, I have my output, and I'm just trying to explain the output based on the input. So I can have, for example, like a deep neural network, which I don't know what is going on in it, and after the fact, I'm just trying to see and explain, oh, well, this is why, you know, Tina's case got this output. And should it be all of these? Should it be none of these? These are things that not just the machine learning algorithm designer should think about, but us as society should think about, right? Perhaps we don't want, when it comes to judicial system, for machine learning algorithms to be used for efficiency purposes. You know, maybe we do, I don't know. I fall on the one that we shouldn't. Or for example, for kidney matching. One of the things that's really popular nowadays, and I'm sure you heard about the study that came out of MIT called Moral Machine, about crowdsourcing morality, right? Ayad Rahwan has done some good work there where like he's looked at millions and millions of people with the trolley problem, right? And so what would you do? Would you hit the cat or would you hit the kid, right? Would you hit the grandma or would you hit the kid, right? Or a bunch of people. There are also people who are doing crowdsourcing in terms of kidneys. So Tina needs a kidney, and so you have crowdsourced like which aspects are important to decide whether Tina should get the kidney first or whether Bob should get the kidney first. These are a little suspect because we know that populism may not be a good thing. In terms of what should the task incorporate, maybe since we're making human decision making, the task should be to learn how a human exemplar makes a decision, right? We have excellent doctors, we have excellent judges, we have, you know, excellent human decision makers for what will happen to you. And what the machine learning algorithm should learn how that exemplar makes decisions, right? So, for example, you have a judge who over the years, his cases have not been appealed that much. His verdicts stand. You're like, oh, this is a person that I should learn how he makes an algorithm who has now learned the decision-making process of this judge. What would you do, right? And in a lot of these cases that you see machine learning being used are cases where you have apprenticeship. In medicine in America, it's very much an apprenticeship. Right? You get your bachelor's, then there's medical school, then there's residency, then there's fellowship, so on and so forth. It's like ducks, right? The same with law, where you go and are your clerk of a judge. And so in machine learning, we do have a way of learning to imitate people, and it's called imitation learning or apprenticeship learning. Now, this is a much harder task than just risk assessment. So let's look at imitation learning or apprenticeship learning and see what it involves. So what you're given is you're given a bunch of demonstrations or a demonstrator that you can follow. And the goal is to learn a policy that will mimic those demonstrations. So the ingredients of apprenticeship learning are the following. You have a demonstrations or access to a demonstrator. So here would be a judge or legal briefs. You have an environment or a simulator. For example, if you're operating in the state of Massachusetts, it would be the state of Massachusetts and its laws and policies. You have a policy or hypothesis class. This is where you're getting into which class within machine learning of models should I pick? Should I pick a deep network? Should I pick a decision tree? Should I pick a 10th order polynomial? What class best represents the policy that I'm trying to learn? You have then obviously a loss function that you're trying to minimize, and then you have a learning algorithm, right? So these are its ingredients, and what you're trying to do is you're trying to learn how a good judge, I don't know, Sonia Sotomayor or whoever you believe is good, how she makes decisions, right? Again, it's a much harder task. And there was a really nice tutorial at ICML, which is the International Conference of Machine Learning in 2018, last year, on imitation learning. And you can go and you can look at the slides and the there's a video there as well. And just in terms of notations, so it becomes more clear for you guys, so you'll have states, you'll have actions, and then what you're trying to do is you're trying to learn a policy that will take you from a state to an action, or from a state to a distribution over the actions. And then obviously you have to worry about the state dynamics, which is if I am at this state and I do this action, what's the probability of going to another state? And so what you're going to be doing is this kind of sequential decision making, which seems to be what, for example, judges or doctors do, where you're trying to learn distributions of states induced by policies, and then more importantly, the trajectories of going from one decision to another, to another, to another. There are lots of different types of imitation learning. I actually won't go through these. But for example, there's behavioral cloning, there's inverse reinforcement learning where you're like, oh, learning a policy is hard, so maybe I have examples of policies and I want to learn the reward. Or you want to do direct policy learning, which has this loop of I'm going to collect demonstrations, I have some supervised tasks, and then I'm going to roll it out in the environment. And I will skip this one in terms of just which one is which. So there are people who have looked at this and have said, oh, this idea of like imitation learning, which is similar to reinforcement learning. So within machine learning, there are 3 types of learning. Supervised learning, right? You have a teacher. Here's Tina. Tina's good. Here's Bob. Bob is bad. So on and so forth, right? And you're basically trying to do function learning, f of x to y. Then there's unsupervised learning where you don't have a teacher. You just have, let's say, homes. You know, this home, number of bedrooms, number of bathrooms, price, location. And then you're trying to group the homes. Or dimensionality reduction. You have too many features, then you're trying to reduce it. Or there's this thing called reinforcement learning where you don't get direct supervision. You do an action, you get a reward, right? And in fact, it seems like most human children learn that way, right? I say to a kid, don't touch that. He touches it. He burns himself. He's like, okay, I shouldn't have touched that, right? So there are people who have thought about applying imitation learning and apprenticeship learning here. The issue is that these are very hard tasks. So if you look into these papers, they're working on very simple problems like a 2x2 grid world, or, you know, is baking a cake better than killing a person? You know, it's like very small problems. So this is something where it will require a huge effort to solve if you actually want to learn the process of decision making. And then the other thing, I think here I'm preaching to the choir, is that perhaps a totally data-driven approach is not the right thing to do, right? Our societies have laws which are constraints, and then the policies are implementations of those laws. And so one of the things that, in terms of a task that would be interesting, would be to try to reconstruct the intent of a policy. In New York City, there was this policy of stop and frisk, right? Where, for example, if somebody looked suspicious, you would stop them and search them and so on and so forth. Now, the intent of the policy was not to stop black and brown kids, but it seemed like that was what it was doing. Right? And so if you can actually show, and again, this is a hard machine learning task, but if you can actually reconstruct the intent of the policy, then perhaps you can make change. And then there are issues in terms of just can we do computational ethics, right? So I went down and I'm coming back up a little bit, surfacing in that, and I highly recommend reading this book if you're interested. It's called Moral Machines. And so they talk about, for example, a bottom-up approach for computational ethics, where you have, for example, a bunch of rules that you want to follow, and well, that could be brittle, or you can have it bottom up where you're learning from examples, and that also has its own problems. And in general, in terms of computational ethics, we should think about whether you can even have a set of logically consistent rules that you can code up to then have a computational system be ethical. Because if you think about ethics, a lot of it has to do with empathy. How do you negotiate through certain conflicts? And this is actually an area that the Department of Defense in America is interested in. For example, if you think about disaster relief or humanitarian aid, you may have a UAV that is trying to deliver water, and the UAV has to decide what to do, whom should he give the water to, right? And it has to incorporate, for example, the cultural norms of the environment, so on and so forth. And then there's some recent work that we're doing, again, circling around with justice reform, where in America the mass incarceration problem is because of state laws. And there's a really nice book by Emily Bazelon recently called Charge that came out. And so the idea is that in America for Bail, so this is pretrial deposition, you're trying to figure out two things. One is flight risk, and one is whether you're dangerous. That is, if I let you out, you will commit a crime. And so perhaps machine learning can be used to determine flight risk. For example, did I take the guy's passport? How long has the guy lived here? Does the guy have a job? Has he shown up for other hearings? But dangerousness is where all the societal bias come in. And so the bar for dangerousness and the use of a machine learning algorithm for determining dangerousness should be much higher. And as my colleague Deborah Ramirez said, bail was not designed and should not be used for crime control. But it seems like that is what it's being done, and that's what the machine learning algorithms are learning for. And then I am part of a Network Science Institute. I like complex networks. And the idea is that should complex social networks be used for these tasks? And the answer, of course, is yes. There are these relational dependencies, right? So between selection and influence, for example, you could say, well, Jack and Jill are similar, so the algorithm should make similar decisions for them. This is actually very much individual fairness. So the people like Cynthia Dwork at Harvard who have worked on differential privacy and are now transferring some of that knowledge into here, into this task of machine learning and ethics and fairness in machine learning. They say, well, if two people are similar in the data space, then the model should predict similarly for them. And then the other one is influence, which is Jack and Jill so are friends, and Jack is bad, so Jill is bad, right? This is where, for example, your mom would tell you, oh, don't hang around with Peter, right? He runs with bad company. So guilt by association. And in particular, one of the things that we're looking at is the dynamics of privilege and prejudice. So if you are a white male, you tend to be privileged all over the world. And so how does that privilege transfer to your friends? And to which one does it stick? And to which ones does it not stick? And the same for prejudice. And here in academia, we know this very well, right? So if you go to a very popular, highly thought of university and work in a very popular and with a highly popular and thought of scholar, then you gain the privilege that that person has, right? But not everybody that goes through that lab gains that privilege, right? And so teasing those apart is interesting and is something that we're looking at. So that was all I had to say about the task. The first thing is the task. You really have to think about what the task is and whether the task is right for whatever you were trying to do and whether you should even use machine learning or not. As I was saying, for example, maybe machine learning should not be used for dangerousness. Or if you're going to use it, then you should, for example, learn how a good human being, how a moral exemplar would do. So do virtue ethics. The other one is experience. There's a lot of people who have done a lot of good work on experience. And so this is the data, right? So the data is bad. So Joy Bugliamani, who just actually testified in front of Congress, she has this frame, this phrase, the undersampled majority. She is at MIT Media Lab, which says that the population is not majority white male, but the training data that's been given to the machine learning algorithm are majority white male, hence the undersampled majority. And so because of that, for example, these commercial facial recognition softwares wouldn't be able to recognize her face. And I was talking to my friend who's at IBM, because IBM software was one of the ones that failed, and so they were trying to figure it out. And he's like, well, I think it has to do with black hair. That's why we can't recognize their face. And I was a little suspicious of that. I'm like, really? You think it's black hair? I don't know. So then there are these things about, for example, when Google labeled a black woman as a gorilla, or the Nikon camera for an Asian person says, did you blink? So these are huge losses for these companies, right? In machine learning, usually people treat loss, as I mentioned, like a loss function, as if there's uniform loss for everybody. But clearly these are not. This is really bad publicity for them, right? And so, again, this is why they're ramping up their data collection so that they don't get this kind of PR nightmare. Then there are cases, for example, in terms of speech, right? Usually Siri or Alexa or these voice recognition softwares do better on a white male than others. Again, it has to do with the training data. Now, in terms of thinking about the experience, should we learn from demonstrations, right? For example, should I set up an agent-based modeling and learn from demonstrations? How would I represent implicit and explicit biases? So there's a really nice paper by Gabby Johnson, who just got her PhD at UCLA and is moving on to NYU, where she talks about the structural bias. And so the way to think about it is perhaps that I have explicit biases and I have implicit biases. My explicit biases are these rules that I follow. And my implicit biases are where, as I go through life, I make these inferences based on my implicit biases, which are just training examples. So I have explicit biases which are represented as rules and implicit biases that are just training examples. And the implicit biases is where we see the most inconsistency in terms of human decision making, right? It's like, wait a second, why did you do that for that case but not that case, right? It's usually because it's not that they're following the rules, because the rules tend to match between one person and another in these, for example, child protective services or so on and so forth, but not the implicit biases that are happening. And should we learn from simulations, and should we learn from social networks? And so from my perspective, we should learn from all of these, right? In particular, since the experience, the data that we're gathering is so lopsided. The other aspect of things is performance measures. So we talked about the task, experience, and now performance measures. This is an interesting and very important aspect of machine learning. And just being one thing that you should be very wary of is accuracy versus intelligibility. So back in, I think this was around 1990s, at University of Pittsburgh, they tried to do the following prediction task. So predict whether serious complications were going to arise from pneumonia. And they actually learned a neural network, shallow neural network, a feed-forward neural network, and it seemed like the neural network was doing really well. But then they looked into it and they saw that the neural network was saying, the accuracy of the neural network was very high. The neural network was saying that if you have asthma, the risk of you having serious complications from pneumonia is very low. That doesn't make sense at all, right? And because if you have asthma and you have conditions of pneumonia and you go to the hospital, they will automatically put you into the ward and admit you, right? And so only like rule-based systems are where they can, when the model is intelligible is when you can figure out what is going on. And especially since people are bad in deciphering correlation and causation, one has to really look into that. So there's lots and lots of different performance measures, like group performance, where the classifier does this similarly on the two groups. There's individual performance and fairness. I mentioned it already a little bit, where like if Tina and Bob are similar, then the model should perform similarly on them. There are these kinds of procedural fairness where you add some rules and properties of the institution. But all of these basically come from like the confusion or the error matrix, which is, what did the model predict and what was the ground truth, which seems very pedestrian. So in terms of the performance measures, all of the current approaches, so if you look at the FAT STAR conference papers or the FAT ML conference papers, a lot of them are trying to put all the normativity into the performance measure, right? And not really changing the task itself. And I think that that is not the right thing to do. And by doing this, they're ignoring any of the normative significance of the task or the experience, right? So what is the right task to learn for, and what should the experience be? And so in terms of take-home messages, so one is that we need to incorporate normativity, or what you ought to do in all aspects of machine learning, both the task, the experience, and the performance. And it seems that the machine learning task of imitation learning or apprenticeship learning, where you're trying to learn the process of the decision-making of a moral human being, of a good exemplar human being, may be a good task to look at, right? And so then when a new person comes in and you have to make a decision about that new person, you would say, okay, what would a moral human being do here, right? And of course, we can disagree on who's good and who's bad, but in many cases, for example, in terms of judges, we believe judges who are good are judges whose decisions don't get appealed, right? And we have those kinds of information. And then since I'm at a university, I want to say a couple of things about education. So there's been lots of college courses in terms of data and digital ethics. There's a whole list of them all around the world. You can get at that Google spreadsheet. Stanford had a really nice course in their winter quarter. I highly recommend looking at that. At Harvard, Barbara Grosh et al. Came up with what they called embedded ethics, where if you have a computer science program or, for example, physics of data program, you would actually build physics into the curriculum. That it's not just one course, but that you actually build it into the curriculum. And this is all great and good, but if you really want to have change, you can't just say, oh, I'm going to teach the physicists or the applied mathematicians or the computer scientist ethics, and then things will be fine. Imagine a master's person that you have taught goes and gets a job at Google, and they're working on something, and he raises his hand and says, excuse me, I think this is unethical. Do you think anybody's going to listen to him? No, right? And so if you really want to have change, you need to teach everybody, right? You need to teach the entire undergraduate population as they go through, how does Google make money? How does Facebook make money? I was shocked that a lot of my colleagues in law and etc., they did not know that Cambridge Analytica could do what it did. They didn't know that if I do this quiz on Facebook, right, that they would have access to my data, right? And so we are working on a course at Northeastern where we teach juniors and seniors about the algorithms that affect their lives. How does Wikipedia work? How does Netflix work, right? Why is it that when you're a woman over 30 in America, Facebook shows you how to lose weight ads, and you can't get rid of it until you change your profile from a female to a male, and then you get a whole other set of ads that you don't want to see, right? Like, why is it that those kinds of things are happening? Now, if you educate the population, then the population can demand that we want certain ethical changes or moral changes. And then there are lots and lots of software packages out there. I'm sure you guys have come across it throughout this course. You can look through them. I like the University of Chicago one because it's my friend Rahid Ghani. He's a lab, social networks. And then the last thing I wanted to say is by Helen Nissenbaum. So people think like all of this work in bias of algorithms and so on and so forth is new. It actually wasn't. So Helen Nissenbaum with Friedman, they had a paper back in 1996. Facebook did not exist. Google was just a twinkle in Sergey Brin and Larry Page's eyes, right? Where she looked at biases in computer systems. She called it computer systems and not algorithms. And they broke it down into societal biases, technological biases, and contextual biases. How does the human decision maker use your computer system? And they have this project called Value in Design. And I like the way that they think about it, which is values in design is a way of considering human life that explores how the values we think of as societal may be expressed in technological designs and how these designs in turn shape our social values. And so if you're building a computer system that people are going to use that are going to affect their lives, you need to think about ethics up front, right? Which goes back to what should the task be? Maybe I can't just go with, simple prediction, right? Classification. Maybe I need to think a little bit more about what the task should be. And then there's some nice papers recently. I just want to highlight one of them. Improving fairness in machine learning systems, what do industry practitioners need? This was recently published at CHI, I believe. It's computer human interactions by folks from MSR, where they did a lot of surveys, and it's a nice paper to read. And I think I'm close to the end of my time. So I want to thank Danielle Allen, who started me. She's the director of ethics at Harvard and said, come on down and give a public lecture that got me going on this. Jack McDevitt, who's a criminologist at Northeastern, Brandon Feidelson, and Ron Sandler, they're philosophers. You can download my slides here as promised. And then these are my contact information. And I'm happy to answer any questions you may have. Thank you for your attention.
Okay, thank you, Tina. I think this was a very stimulating and important talk. So I hope there are questions. Yes, I will try to use this.
Yeah, great talk, by the way. But we know that when a child learns, for instance, to ride a bike or something like that, he learns from experience directly, and then he learns from simulations that are performed during his sleep. And this is being exploited in research for automotive self-driving cars, these kind of things, because we know that humans are still much, much better than automated systems at driving cars. The number of accidents per mile tells that. And so they are trying to teach machines to learn from extreme simulations by doing dreams, where they are confronted with things that they don't encounter in the examples that they are trained with. So my question was concerning your ethics of judging for these things. If there is research in this area being carried forward, because okay, of course you are talking about the undersampled majority class and these things. So if you can enlarge this with simulations, probably, and you can teach ethics through that.
Yeah, the answer is no. I don't know of any groups that are actively working on simulations like that. There were 3 papers that I put up where they talked about, for example, reinforcement learning as an ethical framework. There was a value alignment, and there's also a paper that came out of TU Munich with the robotics that talks about virtue ethics. But if you look into those papers, like they're working on very simple cases, like a 2x2 grid world, like, oh, a robot is going to go into a burning room and collect like a prized possession for me. Nobody, as I know here, has done it in terms of judges. So we're going to start with, Deborah Ramirez, who's a lawyer at Northeastern, she's a law professor, she has very close relations with the court in Massachusetts. And so we're going to go interview judges and get their caseloads and then try to build simulations of them and then try to see how it goes. So come talk to me in about a year, or I'll send it to you in about a year. But it's a very hard task. I mean, if you look at imitation learning or apprenticeship learning, they've been predominantly used for example, being able to drive a car or a bicycle, that kind of stuff. Part of the problem here is that if I want to learn from a judge, perhaps the judge isn't going to tell me like why they made this decision, right, from here to here. And so there could be these incompletenesses, right? And so how do I go from this state to that state? I may take the wrong path and end up at a close state but different and have different results. So it's a very hard task to learn how a human makes a decision, right? And that's what we're trying to start in this. I think it's promising. Okay. Thank you.
The question? Jeff?
So, we certainly wouldn't want to crowdsource how to fly a commercial airliner, right? How are we so certain that if we want to use the information like from the legal system, the American legal system, that this information is really any guidance for us? Like it's almost like you need an assessment of that system to try to figure out if it even is doing what you want, so that you could do imitation learning is to assume you should be imitating it. So how do we, this is this normative question you brought up of where should we think about how to balance between what is showing us how to do something and then would we implement what is better? It seems like a very hard trade-off to figure out how to do in any setting in machine learning.
Yeah, so I guess the way I'm thinking about it is that supposedly the machine learning algorithm in, let's say, judicial cases are being used to help the judge, right? Now, in America, we rate our judges. There is a rating for the judges in terms of like number of appeals they had or so on and so forth. So you could try to see if I build a computer system, how well is that computer system simulating that judge? And then try to see whether I can learn to imitate a good judge better or a bad judge better. In fact, one of the things which is interesting that relates to your question is that maybe the computer system that I should learn should get both cases of the good judges and the bad judges, because machine learning is very good if you give it both of them, right? And so in particular for cases that are in appeal, right, get overturned, those are really good cases to try to learn, you know, what would a moral exemplar do. And so those are cases that we are trying to get more information about right now, where, you know, one judge says this, but the other judge says that, and so on and so forth. So that's how we would do assessments. Because it's not like the judges can make any kind of decision that they want, right? The society puts guidelines on them. It's just that for certain things they have more leeway. Yeah.
Yes.
Hello, Tina. Thank you for your talk. I've got a question about accountability. You mentioned the PR nightmare. So if I'm working with Google and we ship an algorithm that's ugly, that discriminates people, we get a PR nightmare. But what's the accountability with that? I mean, maybe an executive will fall from grace or something. But so recently I heard a statement which I found to be very blunt, which says civil engineers that build bridges that break are accountable for it. They can go to jail, and the same should be valid for computer scientists that build bad algorithms. What's your take on that?
Yeah, you raise a really good question. I mean, so one is that computer scientists haven't had their day of reckoning yet, right? It seemed like at least physicists as a community had their day of reckoning after the atomic bomb was dropped, right? And the chemists had their day of reckoning with the dynamite. Computer scientists haven't had that. If you thought like whatever happened in 2016, what? No. Or if the Uber car killed one person, no, right? And so it is not clear how the law in different countries is going to sort that out, right? It's basically society and the policymakers that have to say, like, is it Tina's algorithm who killed all these people, and so something should happen to her, right? Like, for example, with the Volkswagen debacle, right? The executives said that there was a bunch of rogue software engineers, right? As I understand it, the executives went to jail. Now with, like, Boeing's 737 MAX, that will be interesting to see, right? That, to me, is a very important problem, which is a more societal policy and law question about who is responsible, right? Luckily, right now, as computer scientists, I could put out a software that brings the internet down, and like, nothing probably will happen to me, right? But the accountability is huge. It's a big, big issue. Yeah, I don't have a good answer for it. You have to talk to lawyers from different countries. You know, I'll punt to legal, like most computer scientists do on that one. You know, yeah.
Yes.
I was wondering if you could elaborate a bit on why you think imitation learning is promising. Because if you look at the structure of imitation learning, especially as you cast it in terms of sequential decision making, is not different from learning a sequence of states or events, and that's very standard sort of sequential supervised learning as we do in speech, in video frames or whatever. So why do you expect this to be really better or any different in terms of what you get out of the system?
So there are a couple of things. One is that we should agree on that the machine learning algorithm or the computer system is being used to make a judgment about a human being, right? And that in society we have people that are good at making those judgments, right? And so if I learn to imitate a person who's good at making those judgments, then perhaps my computer system will be less biased than me collecting 30 years worth of data and just shoving it into a system that does classification and doesn't take policies or laws into account. The other aspect of it, which is hard, is this idea of actually learning how a human being makes a decision, right? That is a harder task because I have a lot of partial observability, right? And the state space is very large and so on and so forth. So there's some technical issues there. But the first thing, in terms of directly for your question, is it better that I have a computer program that learns to decide whether somebody should go to jail or not based on what it learns from a good judge or based on 30 years worth of data, right? Which is just some straight up classification. And I think that that is wrong. I think that if you do straight up classification, it's just sorting, right? Versus I want to learn the nuances. And perhaps if we learn the nuances, we could do some of the accountability stuff too. Where it's like, oh, I went from this state to that state, and that's where the whole thing fell apart, right? The decision that I came to was not the right decision. For example, in Massachusetts, there was a guy who was in jail for 4 years under bail. That's like not right, right? And so what was it that led to the guy being in jail for 4 years before like his case came up, right? And so just learning from good and bad judges about how they make decisions seems to be an interesting avenue of research.
Okay, I may ask a question.
Yeah.
Yeah, it's somehow related. Now in Europe we have this GDPR, that is the new law for data regulation and protection. And for example, one of the things that this GDPR says is that there is the right of explainability, in the sense that if there is a decision that is made on me that have been used a machine learning algorithm, I have the right to know basically why this happened. And so speaking with the colleagues and friends, we were somehow thinking that many cases also that lawyers or people from the law presents are basically dominated by supervised learning, where you have tags, you have labels, and then you probably, why is one question, probably because also of the performance, because you have data, because you have this kind of sorting mechanism. And the related question is, are some class of algorithm, let's say, better to satisfy this explainability with respect to other arguments, other algorithms? In other words, should be like kind of a normative role also to indicate a possible kind of algorithm that may be used for purposes, and other kind of algorithm that may be other use of purposes, because these, of course, I might have a higher performance with one kind of algorithm, but I might lose, I mean, explainability and other things that I value. So that's...
yeah, very good question. So, I mean, in terms of explainability, from my perspective, it's really domain specific. So, but a lot of the work, for example, that I'm sure you guys have heard about is like, oh, Tina, this happened to you because you are similar to Jill, right? Or this happened to you because these are the features we were using and these are the weights that were given, right? Which also doesn't put it into context, right? And I think that in terms of human decision making in law or medicine or anything else, the context really matters. The other aspect of it is in terms of the particular domain. I was talking to a lawyer, so a law professor at Yale, and she was telling me that when it comes to criminal justice, people oftentimes feel like they've been treated fairly. If I treat you with dignity, I call you Mr. or Ms. If I give you the time to tell your story, and if I explain to you why something happened to you, right? Like this is happening to you because of law 12392, that's what's going on, right? Which was interesting to me as a computer scientist. I did not know that those were the things that were important. So it was all about treatment. So I think in terms of explainability, one, the domain matters. Two is that usually it seems like people care more about how they're being treated, so explanation about how they're being treated than the impact at the end. And so I feel like with human decision making, since the society puts a lot of constraints on us, it would be models that can take the constraints and incorporate them, right? So basically going back to the old like theory refinement, like for my dissertation, I worked on, well, if I had some theory, can I encode it into a neural network and then learn and refine the theory as I got examples? Now, of course, a neural network, small or large, is not very interpretable. Even a decision tree that's big or long is not interpretable. So then the interpretability goes to like, do I really need a causal explanation, or do I just need to just give them correlation? And in fact, one of the things that computer scientists make I think is a mistake, is they think like causation correlation is just two sides of a coin, which is not actually, right? From my perspective, there's a spectrum, and maybe just robust correlation would be enough to explain to somebody why something's happening to them, and you don't have to actually have causation. In particular, because causal models can be very brittle. So like in America, black people tend to have a higher rate of car insurance, but they also tend to live in places where they don't have enough tax dollars to maintain the street light, right? Or the stop sign is not there, that kind of things. And so you have to be able to build those in, that like, well, why is it that maybe there's more accidents in certain neighborhoods? Maybe it's because the roads aren't being maintained or the lights aren't being maintained. And so it's a tough problem. It's like the accountability problem. So case by case.
Okay, so thank you again, Tina, for the very beautiful talk. And, the next seminar will be on the 6th of June. There will be here Philip Maxner talking about how artificial intelligence are impacting our social and democratic freedom. So we'll wait you for the 6th of June. Thank you.